All right, so what we're going to do is we're going to see if we can lay out a few of the topics in the VCE Specialist Maths Units 3 and 4. Going to create a series of lectures, and this is one of what I expect to be about 95 lectures. So let's jump into it. These are the topics we're going to cover. We're going to cover defining sine, cosine, and tangent, the Pythagorean identity, exact values in radians, graphs of sine, cos, and tan, transformations of those graphs, and features of those graphs. Okay. This is all covered in the methods course, but it's prerequisite knowledge essentially for units 3 and 4 specialist maths. So there's pretty much all of circular functions from methods in one lecture. So I'll put timestamps on the video if you want to go and have a look at specific parts. But the general idea is that I'll cover the big ideas, and then hopefully, with the solid understanding of those big ideas, you'll be able to apply that to a whole range of different problems. And I know it can be helpful sometimes to use examples, and I will where it's absolutely necessary. But if we can think about things in general terms, that allows us to be more flexible in our thinking when we apply that to all different kinds of problems, right? So let's jump into it. Here we have our unit circle. So a unit circle basically has a radius of 1 and it's centered on the origin. So these are the coordinates. This would be 1, 0, 0, 1, negative 1, 0, 0, negative 1. What we want to do is we want to define these sine, cosine, and tangent functions. So what we're going to do is we're going to put a point on the circle. I'm going to call that point P. And at the moment, you can see that has an x coordinate of 0.65 and a y coordinate of 0.76. Okay, what we're going to then do is we're going to connect this point to the origin. So we're going to get a line that's going to look like this. Okay, and then what we can do from there is we can think to ourselves, all right, well, where is this in relation to the origin? Well, it's 0.65 this way and it's 0.76 that way. So we're going to put two sort of lines here. We've got the red line and then we've got the blue line. And you can see that we've formed a triangle. And in that triangle, we can put an angle. At the moment, the angle is 53.13. We can change that to be whatever we like. Now, the angle we're interested in is the angle that's formed from the positive direction of the x-axis to that line. So even though when it comes over here, it reads this angle, the angle we're actually interested in is that angle from the positive direction of the x-axis. It's just the way that this app works on GeoGebra. So let's just leave it there for now. What we want to do is we want to say to ourselves, okay, now let's define this point in space, not by its XY position, but rather in terms of the angle that's created here. It's actually quite a leap in sort of your thinking. You haven't seen this before, but you want to define this point P in terms of the angle here. So how we're going to do that is we're going to think back to our old school um, trigonometric identities. Hopefully you realize that this is a right angle triangle, same as this triangle here. This is the hypotenuse. This is the opposite side. The reason it's the opposite side is it's sort of facing the angle that's created there, this angle theta. And that must mean this side here is what we call the adjacent side, that is adjacent to that angle theta. So hypotenuse longest side, opposite side is sort of opposite the angle there. Okay, and then you've got to think about your trig identity. Sine of theta equals the opposite side length over the hypotenuse. Cosine of theta is the adjacent over the hypotenuse. And tan is the opposite over the adjacent. SOHCAHTOA, TOA, if that rings a bell. So now what we're going to say to ourselves is, okay, let's think about this length here. This length here can be defined as sine of the opposite side, which is this red line, over the hypotenuse length. But since this is a unit circle, this hypotenuse length has a length of 1. So this length here can just be defined as sine of the angle that's here. So let me explain that more. Yeah, so this length here we're going to call sine of theta, and I can assure you sine of 51.07 degrees would be 0.78. Again, because we applied our SOHCAHTOA, the opposite side length over the hypotenuse. So that red line must have a length equal to 0.78 in this case, but if we change it, 0.85 and so on. Okay, the same is true here. If we apply cosine identity, adjacent over hypotenuse, cosine of 48.38 over 1, which is just dividing by 1, doesn't do anything, is 0.66. So this length of this blue line is cosine of this angle here, which is interesting because now we've defined this point in space P not as a coordinate space, but in terms of the angle that's created, the positive direction of the x-axis. So I think that's pretty interesting. The last one is what we're going to look at is the tangent. So if we have a tangent, what we're going to do is we're going to draw a line here. This purple line is obviously a tangent at the point 1, but if we just extend this this line out to that purple line, what we get is you can hopefully see two similar triangles. You can see this sort of bigger triangle here, this one here, and then you've got this sort of smaller triangle inside here. I think you would agree that they're similar triangles. So what that means is the ratio of sine theta, which is this length, to cosine theta, so sine theta to cosine theta must be the same as the ratio of this length from here to here, is to this length, but this length is 1. Okay, and so what we're going to do is we're going to call that the tangent of theta. So this is, yeah, it's simply the ratio of sine theta over cosine theta is equal to what's called the tangent of theta. So that corresponds to this length here when we sort of extend that line out. Okay, so that is how we define sine, cosine, and tangent. With that idea, what we're going to do is we're just going to define the Pythagorean identity as well. So Pythagorean identity, hopefully you're thinking a squared plus b squared equals c squared. And so what we can say is if we look at our triangle that we've created here, same as before, we know that this is sine of theta now. We know that this is cosine of theta. So if we apply Pythagoras' theorem, a squared plus b squared equals c squared, we know that sine squared theta plus cos squared theta must equal 1 squared. But 1 squared is 1. So an interesting fact that falls out of this unit circle discussion is that sine squared theta plus cos squared theta equals 1. And that can be really helpful for solving a whole range of problems. So that's what's known as the Pythagorean identity. All right, so hopefully that's interesting. All right, what we're going to do now is we're going to look at what's called radians. What you'll notice up to this point is we've defined everything in here in terms of degrees, and that's something we're probably a bit more familiar with. There is 360 degrees in a circle. What we're going to do now is going to start to measure angles in a little bit different way, and we're going to use radians. And a radian is the angle subtended by an arc equal to the radius of the circle. So again, this is a unit circle, so this is a radius of 1. If we were to sort of take that radius and place it along the circle such that sort of the distance from that point there around to that point P around the circle was 1, then we would get approximately 57.3 degrees. So around about, I'm not going to get it perfect, it's around about there somewhere. This length, this green length must have a length of 1. And so therefore this is defined in here as 1 radian. Okay, then we can think to ourselves, okay, well, how many radians are there in a full circle all the way around? Well, if you think about the circumference of a circle, the circumference of a circle with a radius of 1 is 2 pi r. But if r is 1, then the circumference of the circle is just 2 pi. So hopefully you can see there must be 2 pi radians in a circle, which corresponds to 360 degrees. So there's 2 pi radians in a circle, which is 360 degrees. So we can say that that's how we wrote it here. 2 pi, we use a superscript c to mean radians, equals 360 degrees. And if we just do a simple conversion here, divide both sides by 2 pi, and then simplify, that we get that 1 radian equals 180 degrees on pi, which is 57.3 degrees roughly. So from now on, what we start to do is we define our angles in terms of radians rather than degrees. And so, just going around the circle, we're going to have 0 radians. Okay, 2 pi radians is all the way around because that's 360 degrees. So halfway around must be pi radians, which means up here must be pi on 2 radians. So that's 90 degrees. Down here, we are 3/4 around the way of a circle with a circumference, with the full lap being 2 pi. So we're actually at 3 pi on 2 here. So another way to think about it, pi on 2, 2 pi on 2, which is pi, 3 pi on 2, 4 pi on 2, which is 2 pi. Okay, and then down here we just have the conversions. So obviously if we want to go from radians to degrees, we multiply by 180 on pi. If we want to go from degrees to radians, we multiply by pi on 180. Okay, and then what we can say from there is there's actually a lot of what's called exact values. So if we look at our exact values, these are key ones that you need to know. So if we're at 0 degrees, that's also 0 radians, and that should make sense. We haven't subtended any arc on the circle. We can think about the sine value. Well, the sine value at that point is just the y value there. So the y value there is 0 because we haven't moved up at all. The cosine value is 1. The tan value, remember tan is sine divided by cos. So that's going to be 0 divided by 1. 0 divided by 1 is 0. So tan of 0 is 0. Okay, then we've got some other important angles. 30 degrees. If I can get it as close as I can, 30 degrees is about there. Okay, if you do the conversion for 30 degrees, you'll get pi on 6 radians. And that corresponds to a sine value of 1/2. Sine value of 1/2, cosine value of root 3 on 2, and a tan value of root 3 on 3. Remember, tan is just sine divided by cos. 1/2 divided by root 3 on 2 is root 3 on 3. Sometimes you'll see this one expressed as 1 on root 3. That's the same thing. That's just this as a rational denominator. Okay, you're probably wondering how we got these values. So either by a calculator or by setting up a triangle with relevant side lengths, you can get these values here. But these are sort of just the key ones we need to know. If we go to 45 degrees and we made a conversion from degrees to radians, we would get that it's approximately, it's not approximately, it's 45 degrees is pi on 4 radians. The sine value there is root 2 on 2. The cosine value is also root 2 on 2. So you notice at about 45 degrees that the sine and the cosine values are the same. And the tan value, again, is sine divided by cos. Anything divided by itself is 1. So the tan value is 1. Okay, 60 degrees is pi on 3 radians. So that's roughly there. There we go. Perfect. And it is the reverse of pi on 6. So you'll notice sine of pi on 3 is root 3 on 2. And you can see cosine is 1/2 or 0.5. Okay. Sine divided by cos gives you root 3. All right. 90 degrees is pi on 2 radians. Sine value there, so the y value is 1. The cosine value is 0 because that's the x value. And then your tan value is undefined because you can't do 1 divided by 0, right? So that is radians and exact values. These must be known off by heart. Okay. Now what we can do is we can start to graph things. So now we've got that point P in space, and what we want to do is we want to graph it. So we sort of thought in discrete chunks there. We went 0, pi on 6, pi on 4, pi on 3, and then pi on 2. But what we need to do is need to think continuously now. So what I mean by that is if we take this point P and let's move it around a little bit. Notice that this point P is moving up. So I think you would agree your P, that length there, that point P, the height of that corresponds to our sine values. So as this increases, our sine values are increasing. So let's just change that up to, let's say, 90 degrees. And you'll notice we're actually going to trace out what's known as our sine curve or our sine graph, right? Okay, we know that sine at pi on 2 is equal to 1. So we're up here, and then so when we're at pi on 2 radians, so we're putting the angle on the x-axis, and then we're putting basically the length of this line on the y-axis. And we can see, again, the length of this line is the sine value, so that represents the sine of the angle, or it represents the length of that line. And so what we do is if we play that, it's actually going to sketch out a graph like this. Oops, one sec. Now let's try that again. So if we play this now, so this is our sine values, right? And I don't know why it's doing that. One more try. So let's see what happens. Maybe I was doing something silly. All right, that's better. So we can see our sine values now. So it sketches out this curve. Notice when it gets to the bottom, sine values are sine value is -1. When it gets back to the x-axis, it's 0. Gets to the top, it's 1, and so on. So we get a curve sketched out like this, right? There's the sine values between -2 pi and +2 pi. All right. What we can do now is we can actually sketch the cosine values. So what that means now is we're thinking about the x value, right? So again, the x position of point P, and we've got the point P, basically the length of this line is being plotted along the y-axis. So if we let that play, see the cosine is going to look like this. Okay. Encourage you to go back and pause the video and think about how it looks a little bit different, but I think you might notice it starts when we're at 0 radians. When we're at 0 radians or 0 degrees, so let's put it to 0 degrees, about there. We have a cosine value of 1. So it starts up here, and then as it goes to 90 degrees, or pi on 2 radians, it goes to 0. And then if we let the whole thing play, it goes to -1 down here at pi radians. 3 pi on 2 goes to 0 again, and then back at 2 pi, which is 360 degrees, back at it's back at 1, a distance of 1, or a cosine value of 1. Okay, so let's do the last one, which is obviously tan. So if we put those lines back in from before and then see what happens. Remember, tan was this length, remember? So remember we had this line from before. That's this length. Sorry, I should say tan is this length from here to here. And so if we let that play from 0 to -360 to 360 degrees, we get something that looks like this. And you might notice it looks a little bit different to the other ones. And again, you'll notice that when P gets to pi on 2 radians, we get it undefined. So we end up having asymptotes at pi on 2 radians like this. And we also get one at -pi on 2, -3 pi on 2, and +3 pi on 2. Okay, and obviously it shoots off, the graph shoots off to infinity because the length of the line, if I pause it, as it goes up here, the length of that line is getting infinitely large. Okay, and then until it becomes undefined. So yeah, we get this cool looking graph for the tangent of x. Okay, let's think about those graphs in a little bit more detail. So we're going to look at sine x first. So if you notice from before, this is just sine x just sketched out more neatly. And what we're going to do is we're going to say, okay, we can transform that graph now. So the general form for a sine graph is what's called a multiplied by sine of n multiplied by x minus h plus k. We'll go through them one by one to see what each one does. If we change a, we get this business going on. So if a is large, you can see that the graph gets bigger. It's like turning up the volume on your TV or on your car radio. It's literally what you're doing. You're sort of increasing what's known as the amplitude. So yeah, that's what A does. And the language you need to know around that is that it is a dilation by a factor of A from the x-axis. Now, from the x-axis, sort of pulling it in this direction, yeah? That's why it's from the x-axis. All right, let's put A back to 1. Let's change the next thing, which is n. So if we change n, if n is large, everything gets squished. Everything gets squished in this direction. So if n is 3, we get sine of 3x. And this is what's known as a dilation by a factor of 1 on n from the y-axis. Remember, y-axis this way, so if we're dilating it by a factor of 1 on n from the y-axis, sort of compressing it and stretching it that way. Okay, so if n is 3, then we've squished all of the x values by 1/3. We've thirded all the x values. Yeah, that's right. Okay, and similarly, when a was 3, let's go back to here. When a was 3, all the y values got tripled. So dilation from the x-axis triples your y values, or changes your y values, should we say? Okay, and then yeah, dilating, if we change n, we're dilating by a factor of 1 on n from the y-axis. Let's put those back to normal. Okay, then let's change h now. H moves everything left and right, so what's known as a phase shift. Okay, if h is positive, so let's say positive 2, you'll notice it says x minus 2 inside the general form. Okay, that's moving everything to the right. If you notice, it's a bit hard to see with the sign graph, but everything here is moving to the right. Okay. K. K moves everything up or down. So K, if K is positive, say positive 3, it's going up, moves up 3. K is negative 2, it moves down 2. So that's how that works there. Okay, whatever K is what's known as the mean line or the line of oscillation, whatever you want to call it. It's basically the line around where it's sort of where the mean line is. So for example, our mean line here is 0, which is the x-axis. It goes up to 1, down to -1, up to 1, down to -1. The average of those two numbers is 0, so we're sort of in the middle there. Okay, let's just put some more technical language around things. So for some graph A sine nx, so we just don't think about horizontal and vertical translations for now, where A is greater than 0 and n is greater than 0, the period is 2 pi on n. Okay, so what that means is the period is the time it takes, or the distance across the x-axis it takes to complete one full cycle. So if we started at the origin and went to here, we haven't completed one full cycle, we would need to go to here to complete one full cycle. And you can see here that that distance from 0 all the way across here to 2 pi is obviously 2 pi. If we change n to be, let's say, 2, we dilate it by a factor of 1/2 from the y-axis. You can see that the period now is pi. 2 pi divided by 2 is pi. So the period is pi in that case. Okay, so that's how that works. The amplitude is equal to the coefficient of the entire function. So in this case, A. So yeah, we call that A. So remember A, it's like turning the volume up. It's called the amplitude. If A is 3 or 4, let's say, the maximum it will reach is 4. And the minimum it will go to is -4. Okay. The range of a function like this is from -a. Okay, so from -a, -4 to +4. The domain, as you can see, is all real numbers. Okay. Now, just be mindful, the range isn't always -a to +a, because if I start to shift things up and down, then the range is going to be k plus a and k minus a. But have a think about that in your own time as well. So yeah, the same is true for cos. So I won't spend heaps of time looking at cosine, but all the same things are true. It just starts at a different point. It sort of starts up here. So again, A dilates from the x-axis, n dilates by a factor of 1 on n from the y-axis. Just another thing to point out, if n is something like 0.5, 1 divided by 0.5 is 2. So if n is 1/2, then it's a dilation by a factor of 2 from the y-axis. So something to be aware of. Other than that, the period is still 2 pi divided by n. The amplitude is a. The range is -a to +a. If there is no vertical shifts. Okay. And yeah, that's why it says this A cos nx, where a is greater than 0 and n is greater than 0. All right, last one, lucky last. Hopefully you're still with me. We're going to look at transformations of tan x. Okay, again, still the same general form here, but tan doesn't make sense to think of tan as having an amplitude. Okay, so when we change a, it's still a dilation by a factor of a from the x-axis, but it doesn't have an amplitude because it doesn't sort of oscillate. So we don't talk about an amplitude for tan, but it is still a dilation by a factor of a from the x-axis. Similarly, if we change n, it's a dilation by a factor of 1 on n from the y-axis, which has the effect of compressing it. If we pick numbers between 0 and 1, it has the effect of sort of stretching it out. So again, if n is 0.5, it's a dilation by a factor of 2 from the y-axis. What else can we say? All right, the period is different. So if we put these back to normal, a is 1 and n is 1. Okay, the period, well, we ask ourselves, when does it start to repeat? Well, we can see if we just look at this first one here, that's sort of going through the origin. -pi on 2 is sort of the left point where it asymptotes, and pi on +pi on 2 is we're at asymptotes on the right. So the distance between negative pi on 2 and positive pi on 2 is pi. So the typical the typical um, uh, period of tan, I'm saying typical, the period of tan is pi. And then so when we dilate it from by a factor of 1 on n from the y-axis, we're taking pi divided by n, not 2 pi divided by n, as was the case here. Okay, so that's that. The range, as you can see, the range is all real numbers. There's nothing, no numbers we can't get in the vertical direction along the y-axis. All right, but the domain is a bit more tricky. The domain is all real numbers, except anywhere where there's an asymptote, right? So we clearly have on this graph here asymptotes at negative pi on 2, pi on 2, 3 pi on 2. And so we use this formula here to tell us where those asymptotes are, where n is this n, right? So all real numbers, not including 2n plus 1 multiplied by pi over 2, where that n value is some integer. So this formula, again, just tells us where those asymptotes are. Maybe I'll just show you that quickly. Yeah, so I just noticed I couldn't use the letter n because I'd already used that letter n. So let's just use the letter p. Basically, what we're saying is that the asymptotes are at 2p plus 1 pi on 2, where p is an element of integers. So I've got a slider here for p. If we change p, you can see that we're going to get our asymptotes at those values. Okay, so interesting to think about. Obviously, that's when there is no... What happens if we change n? Okay, this isn't right. Yeah, I just got rid of n greater than 0 there. N doesn't have an option. If these are the asymptotes, then p is obviously an integer, but these are the asymptotes. If n starts to change, then the asymptotes clearly aren't at that point. So we would need to adjust this by also dilating these asymptotes by a factor of 1/2 from the y-axis. So, yep. Hopefully that's making some sense. Basically, yeah, the asymptote's going to move with the graph, right? So you can clearly see now, hopefully, that the asymptote's at pi on 4 now. So the asymptotes would now be given by 2p plus 1 pi on 4 rather than 2p plus 1 pi on 2. Yeah, but if n is 1, there is no dilation factor, then this is where your asymptotes are. If it's just basically tan x, then this is where your asymptotes are. Okay, hopefully that's making, or A10x if there's any dilation factor, your asymptotes, dilation factor from the x-axis, your asymptotes don't change. Okay, that's an overview of circular functions. That is all essentially prerequisite knowledge for Unit 3 and 4 specialist maths. You need to know how to graph it, you need to know how to solve for the solutions as well. So yeah, go off and practice, and yeah, let me know if you have any questions. Good luck.